And talking about the geometric distribution, we'll first get into our learning objectives. First, we're going to define and apply the geometric distribution to describe the probability of an event occurring over a specified number of trials. And we'll usually be thinking of these of, say, n trials, right? What's the probability of an event occurring over so many trials? What's the probability that I'll have 3 heads over 10 coin flips? But we're going to kind of translate this to time, in which our trial could be a day or a year, that kind of thing. And then secondly, we're going to explore the relationship between the geometric distribution and the risk equation. We might not get to this until Friday. And its design applications. There's also a little bit of a relationship with the Bernoulli, and we'll discuss that because this essentially comes from the Bernoulli distribution, but it's a little bit different. Actually, I'll keep typing a little bit. Well, all right, it's a little bit slower. Okay, so let's introduce it and say we have a Bernoulli trial. And remember, what's the definition of Bernoulli trial? Binary outcome. So success or failure with a certain probability, and that probability could be anywhere from 0.99 down to 0.0001 of the potential outcomes. And then we're going to take n trials of this Bernoulli trial. So we're going to do it n times. And each, of course, has a probability of success of p. And success is however we want to define it. That could be you get a heads or you can get a tails. It could be you have the disease, you don't have the disease. It could be something fails. So success doesn't necessarily mean quote unquote success. So the number of trials the number of trials, big N, which is going to be our random variable, until the first success. Over N trials, which we define. And so that first success occurs for the first time. Follows what's known as the geometric distribution. And I'll write it out and then we'll talk about it a little bit more. So the very simple example is we're rolling 2 dice. How many rolls does it take, or trials, until we get that first double, right? Or that first 7 or something like that. So here's the kind of, we'll just do it this way. What is the probability that the first success is on the nth trial? And the way we would write this is the probability that our random variable n, this is when the first success occurs. So that's our random variable. Big N is equal to little n, which is a parameter that we prescribe. Which we can write as P big N little n. So this would be the distribution function. And that is simply going to be 1 minus P to the n minus 1 times P. And what this says is that we have, so P is our individual probabilities for each Bernoulli trial. And so this is n minus 1 fails, and this is 1 success. Does that make sense? So we get the complement of all the fail, 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 and then boom, we get a success. What is implied in this formulation right here about the Bernoulli trials? So we have fail, we're multiplying it, so that we have this exponent here. So we're saying, okay, say we want to say, what's the probability that they get a heads on the 10th time, the 10th flip of the coin. So we get, so I said heads, so we get tails, 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 tails 9 times, and then we get 1 heads at the end, right? And what am I doing with all of these probabilities to calculate this big probability? So fail, am I adding them together? Am I multiplying them together? Am I dividing them? Multiplying. So if I'm multiplying them, what am I assuming about these trials? Yeah, so each coin flip is independent, and so I get a fail, 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 and I can just multiply these out. So very kind of simplistic approach here. We're just assuming they're all independent, so we can multiply the probabilities. So now we can calculate the moments. We can say that what's the expected value of n? What's the mean number of trials until the first success? And that's going to be equal to the summation. And note I'm doing sums here because this is what kind of a random variable? It's a discrete random variable, n, right? It's just the number, it's a count, it's the number of times. So we start at 1. Do we have a success on the first failure? We go all the way to infinity. Of course, you're going to have a decay here, a geometric decay, essentially. So we're going to multiply all the n's times the probability of that n. So this is just how we do our discrete expected value. And we would just sum them all up. Now, if you do this, you get something that's actually pretty simple, because you're saying n, 1 minus p to the n minus 1 times p, and we're doing it for all the values, you end up with 1 minus p. So just the reciprocal of the probability. And this is a series, right? And there's a series conversion essentially. So if the expected value of n is just 1 over the probability. We're gonna return to that concept a little bit later when we talk about recurrence intervals and risk. So just kind of keep that in your back pocket. The variance of n, if we're interested in that, is equal to the sum, and I won't write everything out, but this is just going to be n minus mu of n squared times n. Oh, sorry, this is times the probability distribution of n. And we know that this is 1 over p from before. So what you end up with when you take that all out is you end up with 1 minus p over p squared. So not too bad. Let's look at the actual distribution, and then we'll talk about how this applies. So here's our random variable. Actually, I'll make that a big N. Here's our PMF, probability mass function. And then all we do is simply apply this equation. So we have P n of n is equal to 1 minus P, so n minus 1 times P. So we can start with 0, and then we can do 1, 2, 3, 4, 5, 6, 7. And if we plug in 0, then we get 1 minus P, so 0 times P. So we just get P. And if we do 1, we get 1 minus P to the 1 times P. So we get, well, I won't factor that out, but I'll just say this is 1 minus P times P. Good. And then so on and so forth. So we'll just kind of keep going down. So this is, I'm kind of drawing it simply as like a linear decay, but it's a geometric decay. So it's not going to be linear. This is a scale that would be a geometric scale. But we'll actually see plots of this and stuff like that. So if we go all the way out to 6, for example, then we're at 1 minus P to the 5 times P. Let's just do a quick example. Actually, let's think about examples. Take a minute, talk amongst yourselves about what other examples of geometric or variables that would follow geometric distribution. So the first success occurs, something happens over so many trials. Come up with a couple ideas with your neighbor. Jaden, what do you think?
I would have to think about it. So I think I'm a little bit unclear. So it's just that after so much time, it's decaying, or it's like after so many trials, it's a fail, or what is it?
Yeah, it's good to get some clarity on that. If we're looking at, say, this value right here, this says that the first success or the first outcome occurs on the 5th trial. So if we go back to the coin flipping example, and we want to, what's the probability of getting a heads on the 5th coin flip? that's what this probability is telling us.
Okay, so could it be like the probability of, say, like hitting a home run on the, I don't know, baseball third
Yeah,
hit or whatever?
yeah. The
Okay.
fifth batter hits a home run.
Okay.
Yeah, totally. And so what's the probability of this particular team, because it's different batters, so what's the probability of this particular team making a home run based on past data? And then we say, okay, in baseball, it's like, okay, you want the fourth batter to hit a home run so that all the other runners make it in, right? And you get all the points. So maybe they'd be interested in the probability that the fourth batter hits a home run.
Okay.
Assuming the bases are loaded, right?
Right.
All right, what do you guys have? So like fifth attempt or sixth attempt, yeah. Okay, so Haley's just, do you play offense or defense? Okay, so Haley's taken 6 shots at the goal. What's the probability that she makes it on the 6th shot? But this one's really specific to the 6th shot. We'll look at the cumulative distribution, and that can tell us what's the probability that we'll make it within the 6 shots. One success within 6 shots, which should be a little bit different. How about you guys?
I'm gonna say not my original idea, just to be honest here, but number of defects in the manufacturing assembly line.
Can you be a little more detailed there, a little more specific?
Expecting 0, 1, 2 widgets before the inspector comes across the active widget.
Okay. So manufacturing. So probability that we have a defect. We'll say 5th widget. I want to see a widget factory sometime. You got one? Okay. All right, great. And we'll just do a very simple example of so here's some examples. We'll say probability that it takes 10 rolls before we roll a double. So 2 dice. Now, I'm really sad because there's a game we play, I think it's in the 2nd class, but we didn't have enough people here to play. And the game is you roll dice and you pass a present around. And when you roll doubles, you get to try to open the presents. It just didn't work out. And it's just, I'm sorry we didn't get to play the game. It's really, but you have to wear kitchen gloves, like oven mitts, to open it. And it's fun. It's a really great game. We'll find a time to play. We'll find the time to play, I promise. It fit in that time, and then we get to talk about rolling dice for the rest of the class, for the rest of the semester. Anyway, we'll play it sometime. Jaden, you can watch, or you can roll. You can get some dice and roll for us, and I'll be your pitch hitter. Okay, so the probability that it takes 10 rolls before we roll a double. Do you know what the probability of rolling a double is? Yeah. So, which, yeah, so this would be a double for the first time, we'll say. So the probability is 6 out of 36, which ends up being 1/6, which ends up being 0.16667. So, and then we have, so that's our P, and then we said N is equal to 10 rolls. So let's just plug this in. This is the probability that N is equal to 10. 1 minus 0.167 to the 9 times 0.167. So what do we get? 0.0, about 32. So the probability that it takes us 10 rolls to get to the first double is 0.032. Now I shouldn't say that. It should say this is the probability that occurs on the 10th roll. Okay, it's just that one thing. We'll look at the cumulative probability in a minute. So this is the probability that doubles occurs on 10th. Now we can go back and look at this distribution right here. This is the PMF, right? What if this is just a generic one? Say we took this all the way up to 10 for our double dice roll example. How would we calculate the probability that N is less than or equal to 10? Just sum them up, right? So it's 0, right? It's well, is it 0? No, I think you have to start at 1. I honestly don't know how to interpret 0 right now. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're just going to add all these up. So this would be the sum. Did I do that already? Oh, I don't know if I did. Sum N equals 1 to 10 of 1 minus P to the N minus 1 times P. And so we get to sum all those up. Probably that it happens on the first roll, on the second roll, on the third roll, on the fourth roll, on the fifth roll. So those are, and when we're adding them up, and therefore we're doing or, right? By adding them up, it's the first roll, or it's the second roll, or it's the, etc. And we know there's no overlap. They're mutually exclusive, so we don't have to subtract out that extra little bit. Okay, let's talk about a way to interpret this kind of from a risk standpoint. And we're going to define a new term called the recurrence. I'm going to say interval. There's a lot of ways to say this. Or return period. I'll just write this out. So say we divide time up into discrete intervals. Such as years. And then we treat each year as a Bernoulli trial. Then we can translate this to the geometric distribution. to describe the probability of an event occurring on or within a certain number of years. Or days or minutes or seconds, right? You can define that time interval as anything you want it to be. So in this case, we could think of an example of, in my neck of the woods, the number of years until a flood of a certain magnitude occurs. Which would be obviously of interest to engineers designing bridges or buildings or something like that. Then we can kind of think about, so the number of years until, right? So it's like this, we have year 0, year 1, year 2, year 3, etc. And then we have the flood occurs right here. So on year 5. So this is the number of years until the first flood occurs. But then we could also think about this time period right here, which we call a recurrence interval or return period. How long does it take if we extend this out between floods? So recurrence interval Ri. Now we're thinking about successive flood events over so many years, right? Over 100 years. What's the average time between these flood events? So on average, the interval between two occurrences should also follow a geometric distribution. So N is the number of intervals until an event occurs. Now we're going to define T as the mean recurrence interval. Or average time, so expected time. Between events. And so we can say T bar is that average time, which would be the expected value of T. So T follows that geometric distribution. And that's going to just be the equation that we showed earlier, which is T is equal to 1 to infinity. T times the distribution of T which is equal to the sum of T times P 1 minus P to the T minus 1. So that's the same geometric distribution as before. And we saw earlier in you can do this by kind of taking the series out. you get essentially, I guess I can just write it out super quick. Do I want to do that? Well, yeah, I'll just write the series out kind of briefly. So you can factor out P, because P doesn't have any T's on it. So it's going to be P times 1 plus 2, 1 minus P plus 3, 1 minus P squared plus etc. all the way out, to infinity. You end up with P times 1 over P squared if you do the series kind of expansion and collapse. And then that gives us 1 over P, which we saw earlier. And so we're defining then T as 1 over P, or T bar as 1 over P, big T. So our mean recurrence interval Ri for recurrence interval, which is the time, average time between two events. Is equal to the reciprocal of the probability of those events. Within a certain time interval in this case. So that's interesting, right? It's what we're saying is if a flood of a certain probability of occurring. So say we have maybe you've heard of the 100-year flood. Have you guys heard of that? This is kind of what's going on behind that, the 100-year flood. The 100-year flood, what this means is we're talking about that's T. T is 100 years. And we're saying that each year, that's the recurrence interval. Each year we have a certain probability of the flood occurring. And the 100-year flood is the flood that has a mean recurrence interval of 100 years. But does that mean the flood happens every 100 years? No. What does that mean, Haley? So on average, and what would that look like? Like, yeah. Or, ultimately you could calculate the probability that happens 2 years in a row, right? So based on what we just defined, what's the probability of the 100-year flood event in a given year? What do you think, Jaden?
Isn't it just 1 over 100?
Yep. So just 1 over 100, which is 1 over T. And so it's just 0.01. And this is the probability of occurrence in a given year. All we're saying is that each year we have a probability of 1% or 0.01. And if we look at a sample of, say, 10,000 years, which we will never have, but I don't know, maybe, we have all these stream gauges on our rivers, and the oldest one now is maybe 130 years, 140 years. So will that stream gauge exist? I think it's on the San Juan. Will it exist in 10,000 years? Gosh, I hope so. I hope our civilization and the US Geologic Survey can continue for 10,000 years. That would be great. The river might be in a very different place at that point. But if we had 10,000 years, then you could look at the recurrence interval, the average time in between floods of a certain threshold, and then say, okay, well, that flood on average happens every 100 years. But we actually know it follows this geometric distribution. So we can go back over here and say, well, that flood on average occurs every 100 years, but it could occur on the 4th year. It could occur on the 5th year, right? There's a probability associated with each of those. So another way to think about this, and this is the way that we're trying to, as kind of flood engineers, communicate the risk of these certain flood events. I'm throwing this thing away, I swear. Okay. We call it what's known as the annual exceedance probability. Or AEP. So the important part is annual. And so for the 100-year events, that's a recurrence interval or return period. This is really what we want to communicate, because people think the 100-year flood, oh, that only happens once every 100 years. Great, we're good. Well, actually, it just has a 1% chance of occurring in a given year, right? That's all we're saying here. And the annual exceedance probability just means it is equal or exceeded. So what is the flood that has a 1% chance of being equaled or exceeded? In a given year. And when we take hydrology, which you guys will, most of you in the fall, then we'll actually look at a stream gauge record and take these and do these calculations with flow. I think I actually did these. Do we do this in a lab? I can't remember. We might. So let's do, we've got 7 minutes. Let's do a quick example together. I'm going to just type this out for the sake of time. This is the example in your book. They give you this geometric distribution example. So we have a building code in a coastal region, Florida, let's say, requires the building design to withstand a wind load. What would a wind load be? What is that? What kind of aspects of winds would we be interested in for wind load? Say we're just measuring wind, like speed. Yeah, so speed, duration. You could think of like, okay, a gust that lasts for 10 minutes versus like hours and hours, right? Hurricane force winds for hours and hours. So there's some more specificity you'd have to get into the wind load. So a certain velocity for a certain time, right? With a return period, also known as recurrence interval. Of 50 years. Another way to think of this is the wind load that occurs on average every 50 years. So that's the kind of recurrence interval definition. What is the annual exceedance probability definition, AP? The annual probability. 1 over T, which would be 1 over 50, which would be 2%, right? So each year we have a 2% chance of seeing this event. Okay, so the first question we could ask is, we could ask a lot of things, but we could ask, what is the probability that the building will experience this wind load on the 5th year? It's kind of a weird question. You know, why does the 5th year matter? When I think about my area of expertise, which is stream restoration, river restoration, a lot of stream restoration is you're kind of designing a channel, you're putting in plants like willows and grass, and giving those plants time to grow and establish so that we have kind of more resistance to erosion is really important. And so from a stream restoration standpoint, I might be saying, okay, I want a flood of a certain magnitude to not occur until after the 5th year, because those 5 years give the vegetation time to establish. Maybe there's another analog to certain kinds of design, like does concrete need so many years to cure for a foundation? I don't know, maybe not. There could be some real examples there of why we might be interested in that. Okay, so let's do this one real quick, and then we'll do another one. So this is on the 5th year. And we'll just go ahead and create this equation. So that's P1 minus P to the 5 minus 1. What is our P? 2%. Okay, so we'll plug that in. So we already did that up here. It's just the reciprocal of the return period. And if we want to find the return period, it's the reciprocal of P. And that gives us 0.018. Kind of close to that 2%, but it's not necessarily related. So this is on the 5th year, the probability that it's on the 5th year. Now we can ask another question. This is probably a little bit more interesting. What's the probability that will occur within the first 5 years? Now this one's a little bit different. How would you write this out? Take a minute to think about this. So probably that N is within the first 5 years, so less than or equal to 5. And because this is an inequality and it's less than or equal to, then we know we're using a cumulative distribution function. So we're going to sum these up. N is equal to 1 to 5. And this is P times 1 minus P to the N minus 1. And then we get all these probabilities. And I'll just kind of write it out just to kind of demonstrate. So we get 0.018, or sorry, 0.2, I guess it is. We get 0.0196 plus 0.0192 plus 0.0188 plus, so you can see they're getting a little bit smaller as we go. 0.0184, which is that it occurs on the 5th year. So this is year 1. This occurs on year 2, year 3, year 4, and year 5, which we already calculated up here. Okay, so that ends up being a probability of 0.096. Another way to do that is we could say, so this is the probability that it occurs less than or equal to 5 times. And we could say this is the probability that, another way to write this is, so this is probably that n is less than or equal to 5. This is equal to 1 minus the probability that it doesn't occur. In 5 years. And how would you write that out? The probability that there's no occurrence in 5 years. Yeah. So this would be 1 minus p to the 5th. And I'll let you calculate that out, but this would be 0.98 to the 5th, and that ends up being 0.096. So just another way to do that. Okay, last thing. This is different from the binomial distribution. And it's easy to kind of confuse these things. The binomial distribution is this would be the probability of exactly one event in 5 years, which is a different question. It's not that does it occur within 5 years, it's exactly one event. How many different ways can we have one success out of 5? And so this would be probability of x is equal to 1 for n is equal to 5. And then we would do the binomial distribution, which would be 5, choose 1, p 1 minus p to the 5 minus 1. So that it ends up being close. 0.092, but it's not the same thing. And I think I have you guys explore the relationship between those two. As your trials get longer, then they kind of converge essentially. All right, thanks y'all.